Welcome to this session on how SDN improves 5G. Today, we will explore how software-defined networking, SDN, enhances 5G networks, making them more efficient, flexible, and scalable. By the end of this presentation, you'll understand how SDN enables automation, security, and dynamic resource allocation in 5G. Let's begin. 5G is the fifth generation of wireless technology, offering speeds up to 100x faster than 4G with ultra-low latency. SDN, or software-defined networking, separates network control from forwarding functions, making networks programmable. Together, 5G and SDN create adaptive, scalable networks that support diverse applications like IoT, autonomous vehicles, and smart cities. Let's take a look at how mobile networks evolved over time. 1G, 1980s, had only analog voice calls with limited coverage. 2G, 1990s, introduced digital voice and SMS, while 3G, 2000s, enabled mobile internet and video calls. 4G, 2010s, brought high-speed broadband, paving the way for streaming and cloud applications. 5G, 2020s, now offers ultra-fast, low-latency, and high-density connectivity for next-gen applications. Traditional network architectures face several challenges. Hardware lock-in forces dependency on specific vendors, limiting innovation. Manual configuration requires administrators to update each device individually, making it slow and error-prone. Traditional networks also have static architecture, meaning resources can adjust dynamically. Lastly, complex management makes it difficult to scale networks efficiently. SDN solves these challenges by introducing a new network management approach. It separates control logic from data forwarding, enabling a centralized software controller to make real-time decisions. This allows programmability, where applications can request network resources dynamically. SDN also provides a global view of network topology, enabling faster, more intelligent resource allocation. SDN is built on four core principles. Programmability allows administrators to modify the network via software updates rather than hardware changes. Network abstraction simplifies management by hiding physical complexity. Centralized control improves efficiency by managing the entire network from one location. Finally, open standards eliminate vendor lock-in, making networks more interoperable. SDN integrates into 5G networks through three main planes: the application plane, where network services define requirements like traffic management and security; the control plane, where the SDN controller makes decisions based on application demands; and the data plane, which consists of physical and virtual switches that forward traffic based on the control plane's instructions. The SDN controller is the brain of the network, maintaining topology information and translating service requests into network configurations. Programmable switches execute forwarding decisions based on controller instructions. APIs, or application programming interfaces, enable communication. Northbound APIs connect applications, southbound APIs control network devices, and east/westbound APIs connect multiple controllers. One of the most powerful applications of SDN in 5G is network slicing. A single physical network is divided into multiple virtual networks, each optimized for specific needs. For example, a healthcare slice prioritizes reliability, a gaming slice minimizes latency, and an IoT slice supports massive connectivity. This allows customized network performance for different industries. SDN plays a crucial role in the 5G core network. It supports virtualized network functions, VNFs, allowing core components to run as software instead of hardware. Dynamic service chaining ensures traffic flows through only the necessary network functions, improving efficiency. Additionally, cloud-native architectures use containerized microservices for on-demand resource deployment. Edge computing in 5G brings processing closer to users to reduce latency. In traditional cloud models, data travels to distant data centers, increasing delays. With mobile edge computing, MEC, processing moves closer to the end user, achieving ultra-low latency below 5 milliseconds. SDN ensures traffic is routed to the optimal edge location, benefiting applications like autonomous vehicles and industrial automation. Security is a major concern in 5G, and SDN strengthens it. Centralized security policies ensure consistent enforcement across the network. Granular traffic isolation keeps security breaches contained within individual network slices. Real-time threat detection enables automatic rerouting of suspicious traffic. Programmable security services allow dynamic deployment of intrusion detection, DDoS mitigation, and encryption as needed. SDN improves quality of service, goes in 5G by dynamically allocating resources based on application needs. For video streaming, SDN prioritizes throughput. For voice calls, it minimizes jitter. For gaming, it ensures ultra-low latency. For IoT sensors, SDN optimizes batch processing, while for autonomous vehicles, it enables instant edge processing for real-time decision-making. In smart cities, SDN-enabled 5G networks provide customized slices for public safety, utility monitoring, and traffic management. SDN ensures that critical services receive priority bandwidth while non-urgent applications operate separately, preventing congestion. This supports real-time traffic control, emergency response systems, and energy efficiency. In industrial IoT, SDN provides redundant pathways to ensure 99.999% uptime for critical manufacturing operations. With response times under 1 millisecond, automated systems like robots and sensors can function in real time. SDN also supports massive device density, allowing thousands of IoT devices to communicate without interference. While SDN greatly improves 5G networks, there are challenges in implementation. Interoperability issues arise as legacy systems may lack SDN compatibility. Skill gaps exist because network teams need software development expertise. Initial deployment costs can be high due to hardware upgrades and software integration. Lastly, performance overhead can occur if centralized controllers introduce latency. The future of 5G SDN will involve AI-driven self-optimizing networks that predict and fix issues before they occur. Intent-based networking will allow administrators to define desired outcomes instead of configuring network rules manually. Open ecosystems will promote interoperability, and zero-touch automation will allow networks to configure and optimize themselves without human intervention. To summarize, SDN transforms 5G networks by enabling programmability, automation, security, and efficiency. It eliminates manual network management, reduces operational costs, and allows for faster innovation. SDN's role in network slicing, edge computing, and security makes it a key enabler of 5G success. As SDN and 5G continue to evolve, new opportunities will emerge in fields like AI-driven automation, cybersecurity, and cloud-native networking. Organizations that adopt SDN early will benefit from greater efficiency, scalability, and cost savings. The shift to software-defined infrastructure is essential for the future of connectivity. Thank you for your time. If you have any questions, feel free to ask. Let's discuss any concepts you'd like to explore further. If you'd like additional resources, visit our knowledge base for white papers, case studies, and implementation guides.